So what we're going to work on today is we're going to go back to 7.1, but we're going to do the B portion. Okay, so unit 7.1B. And this, we're going to learn how to state the domain. State domain of rational expressions. Okay, now stating domain of rational expressions is really, really similar to what we did with domain in our last unit. Okay, our last unit we were doing radical expressions, so that means they had square roots. Okay, this time we're doing rational expressions. So does anyone remember what is a rational expression? Fractions. Okay, so what do we not want to have? Or first off, what is the domain? What is domain talking about? Domain is what? The possible x values. Okay, so domain is all possible values of x. All possible values of x. So if you actually have a graph, you can see what the domain is. Okay, but if you just have an equation, we don't necessarily want to graph everything. So we need to figure out what are the possible values of x. Okay, now, since I said we were dealing with fractions, is there anything that is bad to have in a fraction? Can I have negative fractions? Does that make sense? Can I have negatives in fractions? Yes. Can I have, okay, complex fractions we don't want, but that's not quite what I'm talking about. Can you have positive numbers in fractions? Okay, let's talk about just the denominator of fractions, okay? Doesn't matter, you can have any real number in the top of a fraction, right? Doesn't matter if it's negative or positive. Can you have all real numbers in the bottom of a fraction? You can't? What can you not have in the bottom of a fraction? We cannot have 0. You're right, you can't have imaginaries, but we're just talking about real numbers. Okay, so in the denominator, you can have all real numbers except 0. Because if you have 0 underneath, it gives you undefined. Okay, so the whole point is we do not want our denominators to equal 0. So all we're going to be doing today is we're going to tell you state the domain. State the domain. And you're going to get different fractions, okay, different equations. They're all going to start with f of x, okay? Instead of writing f of x, usually if we were going to graph these, we would just replace f parentheses x with y. So don't worry about what it's equal to, okay? Don't worry about the left side. What we're going to worry about is the right side of the equation, okay? All we're going to deal with is the right side of the equation. So for every single problem, when it says state the domain, yes, x plus 7 over x. Every single problem, when it says state the domain, your answer is always going to be all real numbers except x cannot equal, and you have to solve for it. Okay, what can x not equal here? 0. We do not want x to equal 0. So if it's just an x in the bottom, we always write our answer of all real numbers, but x cannot equal 0. So that means it could be any number except 0 in the denominator. That's your answer for state the domain. Okay, finding domains is actually relatively easy. Okay, so I'm going to show you a couple more examples, and then hopefully we'll kind of catch on to this. Okay, for number 2, if I give you the function f of x equals x squared plus 5x minus 14 over x squared plus 9x. Okay, we do not want the denominator to equal 0. Like this is out of focus. Okay, we do not want the denominator to equal 0. Now, the numerator, the top of the fraction, does not matter at all. Okay, does not matter at all. And your answer is always, we always start these answers off with all real numbers, but then we want to figure out what are the exceptions. I do not want the denominator to equal 0, right? So what you want is we don't want whatever's in the denominator to equal 0. So if you have to solve for x here, how can I do that?
Back
How do I solve for, we factor. So how do you factor this? You get a GCF of x. So x times x plus 9 cannot equal 0. So this is just like solving. We split these up, but instead of setting them equal to 0, we say not equal to 0. So one of your exceptions is x cannot equal 0. What would the other exception be? X cannot equal what? How would you solve? Negative 9. Those are your exceptions. So when you write your answer, you write all real numbers, but x cannot equal 0 or 9. That's your, negative 9. That's your answer for this problem. The domain is all real numbers except 0 and negative 9. Questions? Yes?
So we don't mess with the numbers on top?
You never mess with the numbers on top when we're talking about domain. Okay? What we were doing in the past couple of days is we were reducing. That's when you have to factor, cross things out, that kind of stuff. When we're talking about domain, you only have to worry about the equations on the bottom. Only the denominators. Okay? How about if I asked you to find the domain of x if you, find the domain if you have f of x equals x minus 2 over 4. Any ideas? What's my answer going to be there? All real numbers. Is there any way that my denominator could be 0 here? No, it's always going to be 4, right? So does it matter what I plug in for x? Is the denominator ever going to be equal to 0?
No.
Never. So your answer is just all real numbers. Does not matter what you plug in on the bottom. Okay? So if you think this is easy, good. This should be easy. This type of stuff should be very, very easy. Okay? All you're doing is setting the bottom not equal to 0. So you always put all real numbers and then whatever would make 0 on the bottom. That does not work. Okay, try another one. F of x equals 5 over 2x plus 3. Just state the domain.
Is that an R?
All real numbers. It's not an R, that's how we write all real numbers. So here, your answer is always going to start with all real numbers. And then to find the exceptions, we set the denominator equal to 0, and that's what it cannot equal. So how would you solve for this equation? Subtract the 3, so 2x cannot equal negative 3. And then, how do we get x by itself? Divide by 2, so x cannot equal negative 3 over 2. That's your answers. All real numbers, as long as x is not equal to negative 3 over 2. That is your domain. That's it. Okay? That's what your domain is going to look like. Okay, so there's 4 different kinds that you could have. If you just have a number in the bottom, your answer is always all real numbers. Okay, if you just have an x, all real numbers except for x. If there's something that can factor in the bottom, you have to factor it, set each part equal to 0 and solve. If you have something that's attached to x, you simply solve. Okay, so I don't want you to always think that it's all real numbers except 0. Like in this one, if you plugged in 0, that'd be okay. You wouldn't get undefined in the bottom. So that's okay. Okay, let's try a couple other things. The other part of what you're going to do today is, these are mainly going to be dealing with multiple choice questions. Okay, so your multiple choice question is going to ask, when is this true? Okay, when is this true? And it's kind of going to be like an ABC, like choices here. You're going to say for all numbers, or excuse me, for all values of x, for no values of x, and for some values of x. Okay, you could see it written like this, or you could see it written as always, never, or sometimes. Okay, so these are those always, sometimes, never problems. For all values of x, it's basically saying it's always true. For no values of x, that means it's never true. And for some values of x, it means sometimes. Okay, so I'm going to know, when is the following true? For number 5. When is 16x squared over 10 equal to 8x squared over 5? When is that true? Is that true for all values of x, no matter what we plug in? Is it only true? Is it never true? Or is it sometimes true depending upon what we plug in for x? Okay, there's a couple little guidelines here, okay? If the equation is correct, is correctly reduced, if the equation is correctly reduced, and there are no x's in the denominator. Okay? If the equation is completely reduced and correctly reduced, and there are no x's in the denominator. So, is this equation reduced correctly? Yes. Yes. And since there's no x's in the denominators, your answer is always. Okay? So that means for any value of x, for anything that you plug in for x, this is going to be true because it is correctly reduced. Okay, the next kind that you're going to see are exactly the same thing. Okay, it's going to ask when is this true for all values of x, for some values of x, or for no values of x. When is it true that x plus 7 over x squared minus 49 equals x minus 7? When is that true? That x plus 7 divided by x squared minus 49 is equal to x minus 7. First off, you have to look at, is that correctly reduced? Is that reduced correctly?
No.
No. How should it be reduced? This should be what? This should be reduced as x plus 7. If you factor the bottom, that's x plus 7 times x minus 7. So if you correctly reduced, what should it reduce to be? 1 over x minus 7. So when would this be true? Is it ever true? Never, because it's not reduced correctly. Okay, so this is never true. Okay, never, or you could say for no values of x. Okay, that is never true because it is not reduced correctly. Okay, and you're going to have one more situation that you might see. Okay, something like this. If you have an equation like x squared plus 6x over x squared minus 36 equals x over x minus 6. Why do you think this is a sometimes? Because I did the other ones, right? Okay, you're right. But now I'm going to ask you, okay, I'm going to add some values here. I'm going to give you a couple multiple choices. Okay? I'm going to know, when is this true? For all values of x, for no values of x, for all real numbers except x cannot be equal to 6, or for all real numbers except x cannot be equal to 6 or negative 6. When is this true? Is that always true, sometimes, or never?